Hey everyone, it's Ms. Butler. I'm doing an introduction video on periodic trends, so just some basics, some things that will help us through the unit, and then we're going to talk about Coulombic attraction. Here are the goals or the learning targets for this video if you want to pause and kind of skim through them, but hopefully we cover everything and you feel good about all of these by the end of this short video. All right, the first thing we need to know, and we've probably talked about this in class a little bit already, but it's something called the Octet Rule. And it's the idea that every element wants to have 8 valence electrons and feel like the noble gases. Okay, so those noble gases are the very last column on the periodic table. That group has 8 valence electrons, a full octet, right? And we call them the noble gases. They are the nobility of the periodic table. Everybody admires them. Everybody wants to be like them. So the octet rule is basically all of the elements trying to be like the nobility. That's my crown. Hopefully you like it. Okay, one small exception, hydrogen and helium, they only want 2 electrons in their outermost ring to fill their octet. Again, that is because hydrogen and helium only have that first inside ring. If you picture the Bohr model, here's the nucleus, here's the first ring. Remember, that first ring can only hold 2 electrons. So that is considered full. All of the other rings that we're looking at, we say can hold 8 electrons maximum, right? And so that's why all the other elements want 8. So let's talk about aluminum. If you look at your periodic table, you'll find aluminum kind of over to the right. It's right under boron. So the third period, and then we're past the transition metals. Aluminum is Al. If you look in that column, you should see that everyone in that group has 3 valence electrons. Don't worry if you haven't seen these drawings yet. They're coming soon to a theater near you, but basically it's the symbol with 3 dots for 3 valence electrons. Okay, so aluminum has an option to have a full ring. I can draw aluminum. There's my nucleus. It'll have its 13 protons, but let's put some electrons on these rings. 2 on the first, 1, 2, and then there's 3, 4, 5, 6, 7, 8, 9, 10 electrons, right? 2 on the first ring, 8 on the second, but we know if aluminum has no charge, 13 protons means 13 electrons. So I need 1, 2, 3. So how many valence electrons does aluminum have? 1, 2, 3, and then I just kind of simplified that picture over here if you haven't seen yet with the 3 valence. So it has 3 valence electrons. How many electrons does it need to gain or lose to have a full octet? Well, aluminum has a couple of choices, okay? The first thing aluminum could do is it could pick up 5, right? A full octet means a full outer ring. We could put an electron here, 1, 2, 3, 4. Wait, now we have 1, 2, 3, 4, 5, 6, 7, and then here's 8, right? So there's 5 X's. It could gain 5 electrons to have a full outer ring. Okay, that's possible, but the other option is what if, I'm going to kind of get rid of those X's for a sec. What if we have our normal aluminum with its 13 electrons? What if aluminum loses 3 electrons? So bear with me. What if it loses this, eraser please, this one, and this one? Does aluminum have a full outer ring? Well, remember, this ring is there, but there's also tons more, right? There's a bunch of empty rings, empty space all around aluminum. Just because you have a concert doesn't mean that all of the seats are filled up. That's what's happening with aluminum. Well, is now the outside ring, which is this ring, right? The outside ring is the one that has electrons farthest from the nucleus. That technically is full. Okay, so aluminum has a choice. In order to have a full octet, it can either gain 5 electrons or lose 3. Well, what is easier? It's going to be easier for aluminum to lose 3 electrons, right? That's less work than finding 5. It's basically like kicking 3 people out of the party instead of finding 5 more people to show up, okay? So we know that aluminum is most likely to lose 3 electrons in order to have a full octet. So from now on, I'm going to try to use the vocab. Valence electron is the outermost. So here's my nucleus, got my protons and my neutrons, right? And the valence electrons are any of those outermost electrons. So there's one, here's an outermost. Anything in that ring farthest from the nucleus are called valence or outermost electrons. And you guys should have your periodic tables labeled. It's based off group or columns. So the first column all of them have 1 valence electron. Second column has 2. We're going to skip the transition metals right now. 3, 4, 5, 6, 7, and those noble gas have 8. If you would like, you guys can put variable valence for these transition metals. Okay, so for these 6 elements, I would like you to pause the video and record down how many valence electrons there are, and then try to figure out, will that element gain or lose to have a full octet, and then how many will it gain or lose. And then finally, we'll talk about the charge that the atom will form. So basically, here's what I'm looking for from you guys. Lithium is in the first column of the periodic table. So it has 1 valence electron. Again, I am looking at a periodic table right now. I have ptable.com pulled up on my computer, so you don't need to have this memorized, but I see lithium in the first column. I know it has 1 valence electron. And I'm going to just put 1 dot. Again, you don't have to do the dots yet if you don't want to. Just kind of helps me picture. Okay, does the atom need to gain or lose electrons to have a full octet? Well, lithium has a choice. It could gain 7, right? I could put 7 more electrons, or it could lose 1. If we get rid of that 1 red dot, we would go into an inside ring and still be full. What's going to be easier, gaining 7 or losing 1? Losing 1, kicking 1 out sounds a lot easier. Okay, and then what charge will it form? So let's think. Remember, electrons are negative. So here's how I picture this. Let's say lithium's throwing a party, and there's 1 bad hat, 1 negative personality at the party, right? Someone up to no good, whatever that means to you, great, keep it to yourself. But whatever is within your limits of being negative, bad, causing trouble at this party. If lithium kicks out or loses 1 of those negative people from the party, what is the overall vibe of the party? Well, it's going to be +1, right? If you kick out someone who's causing problems, once they're gone, your vibe is positive. Okay, if you invite negative people to your party, like let's pretend for a second he gains 7 electrons, then our charge would be -7. Okay, that's never going to happen because it's always easier for lithium to kick out 1 bad person. But when you gain electrons, that's like inviting bad people to the party. It makes the whole party negative. But if you kick out or lose electrons, that makes our charge positive. So I would like you guys to try the next 5. Pause the video, and then you can check your answers. All right, hopefully you pause the video and you can kind of check. I noticed for the blue, for the gaining or losing, I put both gain 7 or lose 1, or gain 2 or lose 6 for sulfur, but the one that's circled is the correct answer. I'm just trying to make a point here. Sulfur will never lose 6 electrons. That is not an option. It's only going to gain 2, but I'm just kind of trying to show you how I decide what the best option is, and it's always whatever is less work. Gaining a smaller number or losing a smaller number is what they're going to choose. Okay, and then the charges. Notice sulfur gained 2. That's like inviting 2 bad hats to your party, so a -2 charge. Whereas magnesium loses 2. That's kicking out 2 bad people, a positive charge. And argon, notice, is weird. Argon's a noble gas. Get my crown going. So argon is happy the way he is. He has 8 valence electrons, a full octet. It's going to gain none or lose none. So basically, it's not gaining or losing anything. So we say the charge is 0, or we use the word neutral. So we use the number of valence electrons to help us figure out the charge, right? Are they going to give away electrons and form a positive charge? Or are they going to invite more negative electrons to the party and form a negative charge? So since that's based off valence or outermost electrons, we can relate it to the periodic table because we know there's one valence electron in the first column. So that means all the elements in the first column are likely to kick out that one electron and form a +1 charge. Okay, the second column has 2, they're likely to be +2. The charges vary, just like the variable valence. Then we go +3 on your periodic table. If you do me a favor and make this plus or -4, right, kind of halfway point. We'll talk about that a little bit later. Those guys can kind of depends who they're with. And then we go -3, -2, -1, and those noble gases, those are the nobility. They have 0 charge because they already have a full outer shell. All right, so before we dive into the periodic trends, we need to know about Coulombic attraction. You'll hear about Coulombic attraction in physics as well, but it's basically the attraction of two oppositely charged particles. So I want you to picture a magnet and another magnet. One end of the magnet's usually red, right? And we know that there's some sort of attraction between that positive end of the magnet and the negative end of the magnet, okay? For our class, though, we're not talking about magnets. We're talking about the outermost electrons, which we know are called valence electrons, and those are negatively charged, and the protons, which are positive in the nucleus. So I'm talking about the attraction in an atom between the protons and the valence electrons when I talk about Coulombic attraction. All right, I stole some of these pictures from the Coulombic attraction POGL, so that's kind of what I'm referring to here. I'm not going to go through the questions in the POGL, just talk about some main ideas. Okay, so let's look at distance and attractive force. So what I'm looking at here is the positive protons, so these guys are going to be our protons. And then these are our negative electrons, and these are going to be the valence electrons, the outermost electrons. Okay, so what we have here is we notice from A to B to C, we're changing the distance. NM is for nanometers. That's just a very, very small distance, right? Atoms are very small. So what we're doing here is we're making the distance bigger. Right? From A to B to C, the electron's getting farther away. So when distance goes up, I want to know what happens to the force of attraction between the negative electron and the positive proton. And newtons is just the unit they're using to measure the force. Okay, so 2.3 times 10 to the negative 8th, 0.58 times 10 to the negative 8th, 0.26 times 10 to the negative 8th. As we move the distance farther away, the force of attraction goes down. And I'm going to just call this force of attraction Coulombic attraction. So what do we learn from this picture? As an electron is farther away from the nucleus, the attraction goes down. Well, to me that makes sense. If I take a magnet off my refrigerator right now and I hold it far away, there's not a whole lot of attraction. But when I put that magnet really close to the refrigerator, you can feel the force of attraction, right? So the farther away I pull the magnet, the less force of attraction, the less Coulombic attraction between the fridge and the magnet. All right, if you look at this picture, I have a Bohr model of lithium, a Bohr model of sodium, and a Bohr model of potassium. These are alkali metals. So I'm looking in the first column of the periodic table, and all three of these, I kind of just drew my little periodic table, lithium, then sodium, then potassium, all right on top of each other. Okay, here's some things that I noticed. Lithium has a quantum number of 2. Which basically means for our sake that there are 2 rings, right? So there are 2 rings for lithium. For sodium, it has a quantum number of 3, which means for our sake 3 rings, 1, 2, 3. And potassium has a quantum number of 4, which means it has 4 rings. Okay, as we look, there's more rings for potassium, so as the rings... say number of rings, or the quantum number increases, what happens to the force of attraction, which is Coulombic? Well, if you look, stronger force of attraction means thicker arrow. The arrow is getting thinner and thinner, so force of attraction goes down. Okay, is that consistent with our last slide? Absolutely. As the number of rings, as the distance goes up, the force of attraction goes down, because what we're seeing here is this electron is closer to the nucleus, this one's farther, and this one is the farthest, right? The valence electrons in potassium are far from nucleus compared to lithium. More rings, more distance, which means the force of attraction is weaker. On this guy, the electron's farther away, like the magnet farther away from the fridge. So now let's see if we keep the distance the same but change something else. If you look here, here's my protons. There's 1 proton, 2 protons, 3, 4 protons. And the distance is staying the same. So I notice from A, D, E, F that we're increasing the number of protons. So if the number of protons goes up, what happens to the force of attraction between the outermost, or the valence electrons, and the protons? 2.3 times 10 to the negative 8, 4.6, 6.9 times 10 to the negative 8, 9.2. So those numbers are all getting bigger. So the force of attraction, the Coulombic attraction, is going up. More protons in the nucleus means stronger force of attraction. Think of this as if I'm putting a tiny little magnet here and a tiny little magnet here. What if I put a big magnet in a tiny magnet, and an even bigger magnet in a tiny magnet, and the strongest magnet in the world and a tiny magnet? That's what's happening here. More force of attraction because we have more protons, or think of it as a stronger magnet. All right, same idea here. I have 3 elements, but now they're in the same period, the same row as each other. So we have sodium, and then we'll jump across to aluminum, and then we'll skip a few elements to chlorine. So find those guys on your periodic table, and let's make some observations. Sodium has 1, 2, 3 rings, or for those of you in higher level chem, quantum number 3. Aluminum in the 3rd row, quantum number 3. It also has 1, 2, 3 rings. Chlorine, 1, 2, 3 rings, quantum number 3, 3 rings. Interesting. So they all have the same amount of rings. So we can't really argue that the distance between this electron, the distance between this electron, and the distance between this valence electron, that they're all about the same, right? 3 rings away. But if you look, I can erase my marks, the arrows start to get thicker. So let's look at what's different. Okay, well, we just learned that maybe protons make a difference. Sodium has 11 positive protons. Aluminum has 13 positive protons. And chlorine has 17 positive protons, right? If you look at their atomic numbers, that's where I'm getting the number of protons. Well, does that match? As I increase the number of protons from 11 to 13 to 17, does the arrow get thicker? The force of attraction, or Coulombic attraction, is also going up. More protons, more Coulombic attraction. So here's some Bohr models. The green are the electrons. So they're saying, what do we notice as we go down a group? So let's look down this group. What I notice is that we have the same number of valence electrons, right? 1 outermost, 1 outermost, 1 outermost, 1 outermost. Or you could do it here, right? 2, that's filled, right? Then 8, 8, right? We got 7 outermost, 7 outermost. So same number of valence electrons, but rings, or quantum number, are added, right? If you look, we start with 1 ring, and then 2, and then 3, so we're starting to get bigger. What about as we go across the period? Well, we have different number of valence electrons. Same number of rings. And we increase one positive proton. And that's going to be the key as we go across, right? 3, 4, 5, 6, 7, all the way, one more proton. So same number of rings, but one more proton is added. So here's the big takeaway. Coulombic attraction, remember, which is the attraction between the positive proton and the outermost electron, the valence electron. It depends on the electron's distance. So that's how many rings or orbitals or shells, all of those mean the same thing. Okay, more rings means less Coulombic attraction. Okay, and then the other option, let's say, for example, we have the same number of rings, like they're all in the same row as each other, the same period. Then we look at the number of protons. More protons means more Coulombic attraction. But the key that you need to take away from this is distance dominates. So when you're looking at Coulombic attraction, first see what row they're in, how many rings, okay? We're going to first look at rings. That dominates. The distance dominates. Doesn't matter how strong your magnet is. If you're too far away, it doesn't make a difference. Okay, then if there's a tie for the number of rings, then we will look at protons to decide for strongest Coulombic attraction.